Hello and welcome. In this video, we're going to explore one of the hardest topics for machine learning in 2021. Maybe as a heads up, I have left links in the description below with all the available resources, together with the Jupyter Notebook that we'll explore down the line. Also in the video, there are timestamps, so you can actually jump into whatever section is relevant for you. And that's it. Without further ado, let's begin. So federated learning, also known as collaborative learning, is a new methodology for model training that facilitates the application of machine learning on edge devices, such as smartphones. With this new approach, there is no need for the local data to ever leave these devices, enabling data privacy out of the box. As an illustrative example, is that how you pronounce that?
Illustrative.
As an illustrative example, in most business applications, data is shipped to a centralized location where models can be actually trained. Now, this approach has the strong requirement of which you actually need to have the data locally accessible, at least within the network of access of your computing nodes that perform the training. As a data scientist, you probably download datasets or data from users to your local machine or cloud instance, such as SageMaker or Google Colab, using different frameworks such as Pandas with data frames, or in the case of particularly deep learning, TF datasets. Now, this works just fine when you can actually download the data, but there are scenarios in which this is not feasible or desirable. For example, maybe the data is too large to be held with the current memory and computing capacity of your system, or maybe the data is private and cannot be openly shared. In most cases, the first one can be solved by either horizontal or vertical scaling of your computing infrastructure. The second point is easily addressed by using techniques such as homomorphic encryption or the multi-key variant of homomorphic encryption. What these do primarily is to allow for certain computations to be done over encrypted data without actually having access to the private keys that decipher it. But in this video, we will address these problems from a different perspective. So what if instead of bringing the data to where our computing infrastructure is located, we're actually able to send these computing operations, in this case model training, down to where the data is located, so to where the edge devices are. So the idea is simple. We have a server that coordinates the entire learning procedure and a set of clients that contain the private data. We ship our model from the server down to all the clients, and these clients will independently train the model in their local data. Next, all these models are sent back to the server, which will aggregate the learned parameters. Now, you also have the alternative that if you're not able to perform the training on the edge devices, you can just send the gradients, and the server will aggregate these gradients in a mini batch fashion. Now, neither the learned parameters or gradients are sent as they are, of course, because if you think about it, you can still reverse engineer properties of the underlying dataset from those learned parameters and gradients. Because of that, noise, also known as delta, is added to the sent parameters or gradients to the server in such a way that different gradients kind of cancel out during the aggregation phase in the server. There are different aggregation methodologies. The first one that comes to mind is to just average the learned weights in a neural network across all the learned models in different devices. Now let's take these concepts and put them into practice. We will build our first federated learning application using TF Federated. This is a framework developed by Google that leverages most of the functionality that you will require for building most federated applications. Imagine you're a data scientist that is working for an international banking corporation. You are working on a new iteration of their product in which they want actually to boost user privacy as a marketing campaign for their card. You are tasked with a new iteration of their fraud detection system, with the caveat that now you no longer have access to the user transactions in plain text. Because of this, and you must already know what I'm heading to, you need to rely on training the models at the client side, where the data is located. Worldline has open sourced some of the transactional data for the task of actually performing fraud detection. We will use this dataset as a playground for a federated model. Here we go. So once you open the Jupyter Notebook, in this case I'm using Google Colab, but you can use Jupyter Lab, whatever you have at hand. We're going to be prompted with the program that I just described. So clicking on the Kaggle dataset itself, we can see that this is going to be a binary classification problem. So given a transaction, we want to classify whether it's fraudulent or not. The features that they give us is going to be a PCA encoding of dimensionality 9. So you can consider that the company took a set of features for each transaction and performed PCA over those features, and this is what we got here, from V1 to V9, together with the time. If we want to do this in a federated setting, then we cannot see the dataset as a whole. We need to split it, and for that I'm going to split it in half. So the first half is going to simulate the transactions of one user, and the second split is going to simulate the transactions of another user. So we are going to be, first of all, running through the dependencies and setup, which I already got installed in this particular instance, and then we're going to import all the necessary libraries, together with setting up the seed for reproducibility. Here in TensorFlow, and then down below we're going to do it with pandas in the random splitting and things like that. So once we actually download the dataset from Kaggle, I already got it uploaded here. We're going to load it with pandas, and we're going to see the head of the dataset. So just what we saw before. Only that now, maybe as I made a mistake before, it's actually not 9 vectors, but it's actually 28. So V1 to V28. The amount of cache and the class identifying as fraudulent or not. Now for doing the splitting, very basic pandas indexing. We're gonna take the first half for Alice and the second half for Bob. We are gonna perform some exploratory analysis. Basically, in the first instance, we can see that the transactions amount for only 0.17% of the total transactions. Given this difference in distributions, it's very likely that our classifier is going to be skewed towards the negative class if we don't do anything about it. So we're going to be needing to under or oversample. Maybe the good thing is that if we look at basically the labels for the true splits, there is not a huge difference. So Alice has 269 fraudulent transactions and Bob has 223. One thing that tends to happen in the case of federated learning is that usually datasets are not what you call IID. They're not independent and identically distributed, because by default they come from different people, and different people might have very different distributions. So maybe one thing that we can do before we start modeling is to look into what do the different vectors look like for Bob and Alice, and see if there is a huge difference between those distributions. So that's what I'm doing here. And most of the features, again, you have to consider that these are not all equally scaled. So even though you might see that all of them are the same, there might be quite some differences here and there. But primarily the core difference relies on the time and amount features. When you look into the PCA vectors themselves, they at least follow to a certain degree a similar pattern that we see here being plotted. Moving down to the setup of the model, I'm going to use 100 epochs for training and a batch size of 64. The first step of this entire process is to define the input pipeline. So we're going to go from the raw data in the data frame down to the usable form for training. So this is what this function does here. It takes the data frame as an input, so either Bob or Alice, and it's gonna either it's gonna shuffle it, apply some undersampling for the negative classes, and batch them together. The first thing that I'm doing here is to drop the time feature, simply because I want to keep my classifier as simple as possible and not having to deal with temporal features at this stage. Next, we're going to move into class balancing, in here I'm doing an undersampling of the negative class, so the ones that are not fraudulent. The reason for doing this instead of, for example, oversampling the positive ones is that I'm afraid that given the few samples that we got, it's gonna overfit those positive samples if I basically copy them over and over again. The reason for not doing class weighting within the learning procedure, so in Keras you can actually apply a weight to each sample based on the class in such a way that you could actually balance out how much the algorithm learns from negative samples and how much does it learn from positive samples. And the reason that I don't do that is because, again, the imbalance is pretty huge. We're talking about a 0.17% of positive samples. So there are going to be many of these batches that will not have even a single positive sample. And so overall, that's why I went with the negative class undersampling. So we're going to reduce the number of negative samples to kind of like balance out what the algorithm learns. And the last thing, creating the dataset. So we take that particular data frame and we create the dataset with the features and the values and the labels. And then we batch it into the 64 size. Now, we are gonna be using this methodology within this loop. We're gonna create the training and evaluation datasets using scikit-learn's train test split. So we're gonna have 90% of the data for training and 10% for testing, evaluating. And we're gonna apply again the seed for the random state. So we can actually reproduce the same sampling over different runs. So we append to the training and evaluation data here. Then we define the model. So we are gonna define the input specification in which we define that, hey, we're gonna have 29 features and one label encoding the fraudulent or non-fraudulent transaction. Then the model definition function, we're gonna use a sequential Keras model using dense layers, so a fully connected network, using 32 neurons for the first layer, 64 for the second, and 32 for the third, together with the last one for the output with one single neuron, because we are in a binary classification problem with a sigmoid activation. And then we are going to leverage from the TFF framework, so we can actually create a TFF model directly using this particular method from Keras model. That will define the input, the loss, that is going to be binary cross entropy, and the metrics that I'm interested in. So in this case, it's going to be binary accuracy, precision, and recall. Next, we're going to jump into the training. So again, TFF can leverage many of the operations that we will do using the build federated average process. Using the model function that we have from before, is going to give it a model, And then we're going to define a client optimizer, which in both cases we're going to use Adam. And then we start with the initial state of the model that, if you remember from the previous slide, is going to be like what the server is going to broadcast to all the clients. The clients are going to be training. They are going to compare their new models to the ones that they received. They're going to send back the deltas to the server, and it's going to aggregate those learnings. So this is what is happening here. So for 100 epochs, we perform a training step, so going through a single epoch of data for each client, and then we're gonna append the training history after we're actually done also the aggregation phase in the server. And that's it. We're gonna be running this. So let's go back here where I left off. So TF dataset, pre-processing, defining, and the training. Once we're done with training, we can move into the evaluation of the federated algorithm. In here I create a federated evaluation, again using TFF. And this is going to give us metrics for accuracy, precision, and recall. And in this particular use case, it's going to give us 99.8% accuracy, which, if you saw the imbalance of the dataset, is not really a good metric for estimating how good our classifier is. But for that same reason, I'm putting the precision and recall as metrics. So 67% of precision and 71% of recall, which is not too bad for an initial algorithm. Next, I want to actually see how does the federated algorithm perform in comparison to a model that can see all the data at once, as it was originally intended in the Kaggle competition. So for that, I'm going to concatenate the training and evaluation data of both clients, and I'm just going to put together a basic Keras model using the same hyperparameters. So same network, same epochs, same batch size, same optimizers and everything. So once we do this, we can start with fitting the training data, again waiting for the training to finish. Once that's done, we can move into the comparison of both models. So in here we can see that the single model has, again, a very high accuracy, but then we can see that the precision is quite lower actually. So a 20% precision in comparison to the 67% of the federated learning model. And the recall is a bit higher actually. But overall, when you start looking to the results of papers, something that becomes the norm is that this federated setting actually improves many of the metrics, meaning that it has some regularizing effect on the learning instead of like actually just using the classical mini batch. And I think that's a great thing because it means that we are not sacrificing anything for privacy. In conclusion, we have created our first federated learning model leveraging the easy-to-use TFF API. Decentralized systems can potentially present an alternative to the scenario in which we have one big guy in the middle that orchestrates everything and has all the data. Federated learning opens a door in which we don't need that central point of control anymore, and can potentially solve many of the issues regarding user privacy and data privacy across tech giants such as Facebook. In the next tutorial, we will move this exercise out of the simulation and actually implement a real federated scenario with real clients and real servers using the Flask API. Thank you for watching and see you next time.